May 12th, 1944. The metal detector in Hauptmann Werner Brasch's hand chirped insistently as his salvage team picked through the wreckage near Monte Cassino. The Italian hillside was littered with destroyed equipment from weeks of brutal fighting. American, British, Polish, and German materiel mixed together in a jumbled graveyard of steel and canvas. Brasch's orders were simple: recover any intact American equipment for technical evaluation, particularly communications gear. His team had found plenty of destroyed radios over the past month, shattered SCR-300 tank sets, mangled SCR-510 receivers, crushed SCR-536 handheld units, all worthless for intelligence purposes. But then Gefreiter Hans Müller called out from behind a collapsed stone wall. He'd found something intact, a complete American backpack radio set, apparently abandoned when its operator was evacuated with wounds. The SCR-300 lay where it had been carefully placed, covered with a poncho to protect it from the elements. Brasch approached carefully, half expecting booby traps. The Americans were meticulous about denying equipment to the enemy, but this set appeared genuinely abandoned in haste. He lifted the poncho and examined the radio. The olive-drab metal case showed scratches and dents from field use, but no battle damage. The whip antenna was intact, still attached to its base connector. Most remarkably, the handset and control box were still strapped to the harness. The Hauptmann had seen photographs of the SCR-300 inches intelligence briefings. Wehrmacht communications officers called it the walkie-talkie, using the American slang that had somehow entered German military vocabulary. Reports indicated it was a portable FM radio that allowed voice communication over several kilometers. German intelligence estimated the Americans had produced thousands of units and issued them down to company level. If true, American infantry possessed communications capability that German forces could only dream about. Brasch ordered the radio packed carefully and transported to the nearest technical intelligence facility. The SCR-300 arrived at Testing Station 7 inches Florence on May 15th. The facility, housed in a requisitioned textile factory, specialized in examining captured Allied communications equipment. Oberingenieur Friedrich Hoffmann, who had spent 3 years evaluating American radios, personally supervised the SCR-300's examination. Hoffmann's team began with external inspection. The radio consisted of a metal case approximately 18 inches tall, 8 inches wide, and 10 inches deep, mounted in a canvas and metal packboard harness designed to be worn on a soldier's back. Total weight with batteries was marked as 32 pounds, remarkably light for a radio with claimed 5-kilometer range. For comparison, the German Torn, Fu, D2 portable radio, which provided only 2-kilometer range, weighed 48 pounds without batteries and required an additional 22-pound battery pack. The construction immediately impressed the examination team. The case was heavy-gauge steel with rounded corners to prevent snagging on vegetation. Rubber gaskets sealed every joint and connector opening. The design clearly prioritized durability and weather resistance. Hoffmann noted that American equipment consistently showed this obsession with environmental protection. German portable radios, built to tighter weight budgets, often suffered moisture damage in field conditions. Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The control panel was elegantly simple. A large rotary channel selector allowed the operator to choose from 4 preset frequencies, a press-to-talk switch on the handset-controlled transmission. Volume and squelch controls were clearly marked with instructions in English so simple that, as Hoffmann observed, a child could operate this. Equipment. There were no tuning controls, no frequency adjustments, no technical settings that required operator expertise. The American philosophy was clear. Make equipment so simple that any soldier could use it effectively after minimal training. Opening the case revealed the technical sophistication hidden beneath the simple exterior. The SCR-300 was a complete FM transceiver transmitter and receiver in one unit using superheterodyne circuit design with 18 vacuum tubes. The frequency modulation technology was identical to what German engineers had found in the SCR-300 tank radios, but miniaturized and optimized for portable use. 4 precision quartz crystals controlled the operating frequencies, each ground to tolerances that German factories could barely achieve in laboratory conditions. Lieutenant Karl Schneider, the team's crystal specialist, removed one oscillator for detailed examination. The quartz element was flawless, hermetically sealed in a metal holder with specifications marked precisely on the case. He measured the frequency with the station's precision counter, 47.3 MHz, accurate to within 0.002%. This stability was extraordinary for a portable radio expected to operate in temperature extremes from Arctic cold to desert heat. Schneider calculated that producing 4 such crystals using German methods would require approximately 160 hours of skilled technician time. The Americans were installing them in portable radios issued to infantry companies. With hundreds of American divisions worldwide, the crystal production alone represented manufacturing capacity that staggered the imagination. Where were they getting the trained workers? How were they maintaining quality control? The questions had no comfortable answers. The transmitter section produced 4 watts of FM signal modest power, but the frequency modulation provided significant advantages over the amplitude modulation German radios used. FM signals were largely immune to atmospheric static, electrical interference from vehicle ignitions, and the audio distortion that plagued AM communications. The American operator could communicate clearly in conditions that would make German radios unintelligible. More impressive was the receiver sensitivity. The team connected the SCR-300 to a signal generator and measured its performance across the entire frequency range. The receiver could detect signals as weak as 0.5 microvolts sensitivity, comparable to the best German laboratory receivers, but packaged in a backpack portable unit. Hoffmann's report noted that this sensitivity, combined with FM's noise immunity, explained how American forces maintained communications over distances that should have been impossible for low-power portable radios. The power supply system revealed another dimension of American engineering sophistication. The SCR-300 operated on standard BA-70 batteries, large, dry cells that provided 103.5 volts for plate supply and 1.5 volts for filaments. Battery life was specified as 10 hours of normal use, defined as 1/4 time transmitting, 3/4 receiving, and standby. German portable radios typically achieved 4 to 6 hours on battery power before requiring replacement or recharging. But it was the voltage regulation circuits that truly impressed the examination team. American designers had included automatic voltage control systems that maintained stable operating voltages as batteries discharged. This meant the radio's frequency stability and output power remained constant throughout the battery life. German portable radios suffered significant performance degradation as batteries weakened, often becoming unusable long before batteries were completely exhausted. The modular construction philosophy, evident in the SCR-300 tank radios, appeared again in the SCR-300, but adapted for field maintenance. Major subassemblies transmitter, receiver, power supply, and control unit were separate modules that could be replaced without tools by following simple procedures in the technical manual. A company communication sergeant could swap a failed receiver module in minutes, sending the damaged unit back to depot facilities while keeping the radio operational. This approach required enormous manufacturing capacity to produce spare modules, but it solved the fundamental problem of maintaining equipment under combat conditions. German portable radios required trained technicians to diagnose and repair failures. Component-level repair in field conditions was difficult and time-consuming. When a radio failed in combat, it often remained inoperative until withdrawn to depot facilities, if those facilities still existed and could be reached. The examination team spent 2 days testing every function of the SCR-300. They connected it to a monitoring station 8 kilometers away and established clear voice contact using only the standard whip antenna. The FM signal remained intelligible even when they deliberately introduced electrical noise from a gasoline generator running nearby. The German Torn. Fu, D2, tested for comparison, could barely reach 3 kilometers under ideal conditions and became unintelligible with even modest electrical interference. Range tests in rough terrain proved even more revealing. The team carried the SCR-300 into the hills outside Florence, establishing contact from positions that German doctrine would have considered beyond portable radio range. The FM signal propagated effectively over obstacles and through vegetation that would have blocked or severely attenuated AM signals. American infantry, equipped with these radios, could maintain communications in terrain where German units would be isolated and unable to coordinate actions. Hoffmann's preliminary report to Wehrmacht High Command, transmitted on May 20th, 1944, was blunt in its assessment. The SCR-300 represented a capability that German forces simply did not possess and could not replicate with existing resources. American infantry companies maintained constant radio contact with battalion headquarters under all conditions. German infantry relied on telephone wire, messenger runners, and visual signals methods that broke down rapidly under combat stress. The report estimated that the Americans had already produced at least 50,000 SCR-300 units, possibly more, with American divisions numbering in the 90s and growing, and with each division requiring hundreds of portable radios. Production must be running at thousands of units monthly. German production of comparable equipment, though no truly comparable equipment existed, was measured in dozens of units per month. More disturbing was the continuous improvement evident in the captured SCR-300. The serial number and date code indicated manufacture in early 1944. The team had access to intelligence reports on earlier SCR-300 models from 1942 and 1943. Comparison revealed numerous small improvements: better seals against moisture, redesigned battery contacts, modified circuits for improved stability, enhanced receiver selectivity. The Americans were not just building equipment in quantity, they were systematically improving it based on field experience and incorporating lessons learned into ongoing production. The technical examination of the SCR-300 answered questions about American communications capabilities, but it raised even more troubling questions about American industrial capacity. Oberingenieur Hoffmann's team shifted focus from analyzing the radio itself to understanding how such equipment could be mass-produced. The answers, derived from captured manuals, production documentation, and intelligence reports, painted a picture of industrial mobilization that Germany simply could not match. The SCR-300 was designed by Galvin Manufacturing Corporation of Chicago, a company better known by its trade name, Motorola. Before the war, Motorola had been a medium-sized manufacturer of automobile, radios, and home receivers. In 1940, the company employed approximately 1,000 workers. By 1944, employment had grown to over 8,000. The company's Chicago facilities had expanded from a single building to a sprawling industrial complex, producing military radios, walkie-talkies, and electronic equipment in quantities measured in tens of thousands monthly. This transformation was not unique to Motorola. Across America, dozens of companies had converted from civilian production to military manufacturing. Philco, a Philadelphia radio manufacturer, produced SCR-300 units alongside Motorola. So did RCA, Stromberg Carlson, and several others. The American government had deliberately created multiple production sources for critical equipment, ensuring that bombing or sabotage at one facility could not cripple production. German intelligence estimated total SCR-300 production capacity at approximately 5,000 units monthly across all manufacturers. This figure, if accurate, meant that American factories could produce more portable radios in 6 months than Germany possessed in its entire military inventory. The implications for battlefield communications were staggering. American forces would never lack radios. Units could replace damaged equipment immediately. Older models could be retired to training units as improved versions entered production. The production documentation captured with the SCR-300 revealed the methodology behind this manufacturing miracle. The technical manual included complete parts lists, assembly procedures, and quality control specifications. Every component was identified by a standardized part number and military specification. This standardization meant that components from one manufacturer could be used in radios built by another manufacturer. A transmitter tube made by RCA worked identically in a Motorola-built or Philco-built SCR-300. Hoffmann's team analyzed the parts list in detail. The SCR-300 contained 18 vacuum tubes of 12 different SIO types. Every tube type was standard across multiple radio designs. The same tubes appeared in SCR-508 tank radios, SCR-284 infantry sets, and various other equipment. American factories could produce these tubes in enormous quantities because demand was consolidated across all radio types. German radios, in contrast, used custom tube designs specific to each equipment type, forcing manufacturers to maintain dozens of low-volume production lines. The crystal oscillators presented the same pattern. The 4 crystals in the SCR-300 used standard HC6 U holders, a military specification that defined exact physical dimensions, electrode configurations, and frequency tolerances. Any American crystal manufacturer could produce HC6 U crystals that would work in any radio designed to use them. This interchangeability was the key to mass production. German crystal production remained a laboratory art. Each crystal was individually grown, cut, ground, and tested by skilled technicians. Specifications varied between equipment types and even between production batches. Field technicians could not simply swap crystals between radios. Each crystal was effectively unique to its specific equipment. This artisanal approach ensured high quality for the units that were produced, but it made mass production impossible. The capacitors, resistors, transformers, and other passive components in the SCR-300 followed military specifications that defined electrical characteristics, physical dimensions, and reliability requirements. These specifications created enormous economies of scale. A factory producing capacitors to military specifications could sell them to dozens of radio manufacturers, building hundreds of different equipment types. Production quantities reached millions of units monthly, driving costs down and quality up. The assembly procedures, documented in the SCR-300 manual, assumed that workers had minimal technical training. Each step was numbered and illustrated. Torque specifications were provided for every screw. Color coding identified wire connections. The entire process was designed so that semi-skilled workers could assemble complete radios without understanding radio theory. Quality was built into the process through fixtures, jigs, and test procedures, rather than relying on craftsman skill. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. This approach contrasted sharply with German manufacturing philosophy. German radio production relied on skilled radio technicians who understood circuit theory and could hand-adjust components to achieve optimal performance. This produced excellent individual radios, but it could not scale to the quantities modern warfare demanded. Training a skilled radio technician required years. Training a worker to follow assembly procedures required weeks. The testing procedures revealed another dimension of American industrial sophistication. The SCR-300 production manual specified automated tests at each assembly stage. Transmitter modules were tested for frequency accuracy, power output, and modulation quality, using automated test equipment that measured all parameters in seconds and printed pass-fail results. Workers did not need to interpret measurements. They simply read the printed result and either passed the module to the next station or sent it to rework. German factories relied on manual testing by trained technicians. A skilled operator would connect test equipment, make measurements, interpret results, and decide whether a radio met specifications. This process was slow, expensive, and vulnerable to operator error. It limited production to the pace of the slowest tester and required maintaining a staff of highly trained technicians who could better serve in combat units or design positions. The captured SCR-300 included a maintenance manual that documented field repair procedures. The manual was remarkable for what it did not include. There were no component-level troubleshooting guides, no circuit theory explanations, no adjustment procedures for aligning RF stages or tuning intermediate frequency transformers. Instead, the manual provided decision trees. If symptom X occurs, replace module Y. If that doesn't fix the problem, replace module Z. This module replacement approach meant that company-level maintenance personnel could keep radios operational without understanding electronics. Failed modules were sent to depot facilities staffed by trained technicians with proper test equipment. Depot personnel could perform component-level repairs, or, more commonly, simply scrap failed modules and issue replacements from inventory. The entire system assumed unlimited manufacturing capacity to produce spare modules. Hoffmann's May 30th supplementary report focused on industrial implications. He estimated that matching American SCR-300 production capacity would require Germany to build at least 15 new factories, each employing 3,000 to 5,000 workers. These factories would need specialized equipment for tube production, crystal grinding, component manufacture, assembly, and testing. Raw materials, particularly high-purity quartz for crystals and rare elements for vacuum tubes, would need to be secured from sources Germany no longer controlled. Even if the factories could be built and materials secured, the workforce presented an insurmountable challenge. American factories employed tens of thousands of semi-skilled workers, many of them women, who could be trained in weeks. German radio production required skilled craftsmen with years of training. These men were increasingly drafted into combat units as manpower shortages worsened. Replacing them with semi-skilled workers was impossible because German equipment was not designed for assembly line production. The timeline was equally discouraging. Hoffmann estimated that even with unlimited resources and highest priority, Germany would need 3 years to match current American SCR-300 production capacity. By then, the Americans would have moved on to newer, better equipment, while continuing to produce existing designs in even greater quantities. The industrial gap was not just wide, it was growing wider every month. The examination team investigated American training procedures by analyzing captured field manuals and interviewing German soldiers who had fought against American units. The pattern was consistent. American radio operators required minimal training. Most could effectively operate an SCR-300 after just 2 weeks of instruction. German radio operators needed 6 months to a year of training to achieve comparable proficiency with more complex equipment. This training differential multiplied the industrial advantage. America could produce thousands of radios monthly and train thousands of operators monthly, expanding communications capability at a pace Germany could not match. When American operators became casualties, replacements arrived quickly with adequate training. When German operators were lost, their specialized skills were irreplaceable. The crystal production bottleneck received particular attention in Hoffmann's analysis. He documented that American factories were producing approximately 50 million precision crystals annually across all types and frequencies. This estimate was based on captured production records, serial number analysis, and intelligence reports on American crystal manufacturers. The figure seemed impossible. It represented more crystals than Germany had produced in the entire history of radio manufacturing, but multiple independent sources confirmed it. American crystal production had been industrialized through a combination of automation, standardization, and sheer scale. Companies like Bliley Electric in Pennsylvania operated factories where precision grinding machines, operated by workers with minimal training, produced thousands of crystal blanks daily. Automated testing equipment checked frequency accuracy. Statistical quality control identified production problems before thousands of defective units were produced. The entire process was designed for volume production. German crystal production remained artisanal. Individual technicians ground crystals to specification using manual equipment. Each crystal was individually tested. Production rates were measured in dozens per technician per day, not thousands per machine per day. German crystals were arguably superior in ultimate performance, hand-selected and individually optimized, but this quality advantage was meaningless when the Americans could produce 1 million adequate crystals for every perfect German crystal. The technical specifications of the SCR-300 were impressive, but specifications meant nothing without field validation. Oberingenieur Hoffmann's team conducted extensive range testing throughout June 1944, comparing the American radio against Germany's best portable equipment. The results were so one-sided that they initially questioned their own measurements. Multiple tests confirmed the same devastating conclusion. The SCR-300 achieved ranges that German portable radios simply could not match. The baseline comparison pitted the SCR-300 against the Torn Fu D2, Germany's standard infantry portable radio. Both were backpack-carried FM transceivers designed for company-to-battalion communications. On paper, they seemed roughly comparable. In practice, the performance gap was enormous. The Torn D2 achieved reliable voice communication to approximately 2.5 kilometers under ideal conditions, flat terrain, clear weather, elevated antennas at both ends. The SCR-300 routinely reached 5 to 8 kilometers under identical conditions. This wasn't just a 2x advantage. It was the difference between functional tactical communications and isolated units unable to coordinate actions. Terrain: the Italian mountains where so much fighting occurred, the SCR-300 maintained contact across ridgelines and through valleys where the Torn Fu D2 lost signal completely. American companies could spread out over much wider frontages while maintaining continuous communication with battalion headquarters. The examination team initially suspected that the Americans were using higher transmission power. They carefully measured the SCR-300's output, 4 watts, as specified. The Torn Fu transmitted 2 watts, half the power, but nowhere near enough to explain the dramatic range difference. Something else was at work. The answer lay in the fundamental differences between frequency modulation and amplitude modulation, and in the superior receiver sensitivity of American equipment. FM signals possess an inherent advantage in overcoming noise and interference. In AM radio, signal strength and noise add together, weak signals disappear into background static. In FM radio, the frequency modulation process provides what engineers call capture effect. The stronger of 2 signals on the same frequency completely dominates the receiver output, suppressing weaker signals and noise. This meant that FM radios maintained clear communication even when signals were relatively weak. The SCR-300's receiver sensitivity amplified this advantage. The American receiver could detect and demodulate signals as weak as 0.5 microvolts, about 1/10 the minimum signal the Torn Fu D2 required. This sensitivity meant that SCR-300 seconds could communicate reliably over distances where the received signal was barely above noise level. The combination of FM's noise immunity and superior receiver sensitivity produced the remarkable range advantage German testers observed. Hoffmann's team conducted systematic range tests in various terrain types. In flat, open country near Florence, 2 SCR-300 seconds maintained clear voice contact to 8.2 kilometers, using only their standard whip antennas. The signal was strong enough that operators could communicate without repeating themselves or using phonetic alphabets. Torn 2. D2 radios tested identically in the same locations achieved just 3.1 kilometers before signals became too weak for intelligible communication. In hilly terrain, the advantage expanded further. The SCR-300 maintained contact across ridgelines and through valleys to distances exceeding 6 kilometers. The Torn, Fu, D-2 lost contact at approximately 1.8 kilometers when terrain blocked line-of-sight propagation. This difference was tactically decisive. American units could disperse across complex terrain while maintaining communications. German units had to stay tightly concentrated or lose contact with higher headquarters. Urban testing in Florence's damaged buildings revealed similar disparities. The SCR-300 penetrated concrete structures and maintained contact through multiple walls and floors. The Torn, D2 signal attenuated rapidly in building complexes, often failing to maintain contact between adjacent city blocks. Urban combat required close coordination between units, exactly the situation where the German radios performed worst and American equipment excelled. The weather resistance tests proved equally discouraging. Hoffmann's team operated both radios in heavy rain, finding that the Torn, Fu, D2, suffered significant performance degradation as moisture penetrated seals and affected circuits. Range dropped by approximately 30% in wet conditions. The SCR-300, with its superior sealing and moisture-resistant construction, maintained full performance in heavy rain and even continued functioning after being briefly submerged in a river. This reliability advantage meant that American units maintained communications in conditions where German radios simply failed. Artillery forward observers, equipped with SCR-300 seconds, could call for fire support in any weather. German observers with Torn, Fu, D2 radios often lost contact during the storms and rain that were common in Italian mountain campaigns. The tactical implications were obvious and devastating. The examination team interviewed German prisoners who had fought against American units to gather field observations about enemy communications capabilities. The reports were consistent and alarming. American infantry companies maintained constant radio contact with battalion headquarters, regardless of conditions. Forward observers appeared to have unlimited ability to call for artillery and air support. Even squad leaders sometimes carried portable radios, allowing them to communicate directly with company commanders. German infantry, in contrast, relied primarily on telephone wire for communications. Wire was vulnerable to artillery fire, tracked vehicles, and simple bad luck. When wire broke, which happened constantly in combat units lost contact, radio backup existed, but portable radios like the Torn, Fu, D2, could not reliably reach beyond 2 to 3 kilometers. Forward observers often lost in contact with artillery battalions. Attacks broke down because assault companies couldn't communicate with reserves or supporting units. One captured German officer, a company commander who had fought in Italy for 6 months, provided particularly valuable testimony. He explained that his company's Torn, Fu, 2, radio had never successfully maintained contact with battalion headquarters during actual combat operations. The combination of terrain, interference from artillery, and the chaos of battle always degraded performance below usable levels. His company relied entirely on runners to communicate with higher headquarters, a method that introduced delays of 30 to 60 minutes for critical messages. He described watching American units operate during a lull in fighting. An American company occupying adjacent positions maintained constant radio contact. Company commanders talked to battalion headquarters continuously. Platoon leaders used portable radios to coordinate movements. Forward, observers called for artillery adjustments in real time as German units maneuvered. The American communications network functioned so reliably that they treated radio contact as a given, not a luxury. This officer's most striking observation concerned casualty reporting and medical evacuation. When an American soldier was wounded, his unit could immediately radio for medical assistance. Medics arrived within minutes, often with precise information about the casualty's location and condition. German units had to send runners to request medical support. By the time help arrived, if it arrived, wounded men had often bled to death from injuries that might have been survivable with faster evacuation. Hoffmann incorporated these field observations into his comprehensive report dated June 28, 1944. The document ran to 156 pages of technical analysis, test results, comparative data, and strategic assessment. The conclusions were unambiguous and devastating. The SCR-300 provided American infantry with communications capabilities that German forces could not match with existing equipment and could not replicate with available resources. The range advantage alone, 5 to 8 kilometers versus 2 to 3 kilometers, meant that American units could operate effectively across frontages twice as wide while maintaining coordination. This translated directly to battlefield effectiveness. American battalions could spread companies across wider areas, making them harder to target with artillery and harder to pin down with tactical maneuvers. German battalions had to keep units concentrated within 2 to 3 kilometers of headquarters to maintain any hope of radio contact. The reliability advantage multiplied the range advantage. American radios worked in rain, mud, heat, and cold. They survived rough handling, maintained performance as batteries discharged, and continued functioning under conditions that disabled German equipment. This meant that American communications stayed operational during the critical moments of combat when German networks broke down. The simplicity advantage addressed a problem that German doctrine largely ignored. Combat radios were operated by combat soldiers, not communications specialists. The SCR-300 could be effectively used by infantrymen with minimal training. The Torn. Fu. D2 required trained radio operators who understood frequency adjustment, antenna tuning, and troubleshooting procedures. When those operators became casualties, the radios became useless to whoever inherited them. Hoffmann's report calculated the industrial resources Germany would require to field equipment comparable to the SCR-300. The estimates were staggering. Production capacity for 5,000 units monthly would require 15 to 20 new factories, employing approximately 75,000 workers. Raw materials would include 20 million precision crystals annually, 100 million vacuum tubes annually, and quantities of copper, aluminum, and rare elements that Germany could no longer access. Even if resources could be found, the timeline made the effort pointless. 3 years minimum to build factories, establish production lines, and reach full-rate manufacturing. By mid-1947, assuming Germany somehow survived that long, American forces would have moved on to newer equipment while continuing to produce SCR-300 seconds for secondary theaters. The industrial gap would not narrow, it would widen. The training differential was equally insurmountable. Germany would need to train 100,000 radio operators annually to support widespread SCR-300 equivalent deployment. Each operator required 6 months of training with existing German radio doctrine. That meant 50,000 men in training at any given time, men desperately needed in combat units. The Americans trained SCR-300 operators in 2 weeks, allowing rapid expansion of communications-equipped forces. Hoffmann's final assessment was brutally honest. Germany had no path to communications parity with American forces. The industrial capacity gap, technological sophistication gap, and training efficiency gap were too large to overcome with available resources and time. German infantry would continue fighting with portable radios that achieved 1/3 the range of American equipment, worked reliably only in ideal conditions, and required trained operators who were in desperately short supply. The report's strategic implications section addressed what German commanders should expect in future engagements. American forces would maintain superior communications under all conditions. They would coordinate movements more effectively. They would employ artillery and air support more efficiently. They would maneuver over wider frontages. They would sustain operations in weather and terrain conditions that degraded German communications. Offsetting these advantages would require compensating in other areas where Germany was also outmatched. Superior training required time and trainers that didn't exist. Superior tactical skill required experienced officers and NCOs being lost faster than replacements arrived. Superior equipment in other domains required industrial capacity diverted to match American communications advantages. There were no comfortable options. The report reached Wehrmacht High Command in early July 1944. It was classified most secret and distributed to fewer than 24 senior officers. The response was minimal. No crash programs were authorized. No new factories were planned. The implications were simply too devastating to acknowledge. Germany would fight on with inadequate communications, accepting tactical disadvantages that multiplied across every engagement. Oberingenieur Friedrich Hoffmann continued examining captured American equipment through late 1944 and into 1945. Each new example reinforced the same conclusion. American industrial capacity had made technological superiority militarily decisive. The SCR-300, a backpack radio that weighed 32 pounds and provided 8-kilometer range, symbolized everything Germany could not match: mass production of precision equipment designed for operation by minimally trained users. In April 1945, as American forces overran the testing facility in Florence, Hoffmann was ordered to destroy all classified documents and equipment. He carefully dismantled the captured SCR-300 that had been the subject of so much analysis, removing the 4 crystal oscillators and securing them in his personal kit. The crystals, each representing 40 hours of German technician labor to duplicate, became his personal souvenirs of Germany's defeat. Years later, working as a consultant to American electronics companies, Hoffmann would explain to engineers how German technical experts had recognized American superiority, reported it accurately to superiors, and understood its implications. The warnings went unheeded, not because German leadership was incompetent, but because the truth was simply too devastating to accept. How do you tell an army that the enemy's backpack radios are technologically superior to your best equipment and that you possess no industrial capacity to close the gap? The SCR-300, with its 8-kilometer range that German portable radios could only dream about achieving, represented more than just better engineering. It represented a complete industrial philosophy designed for manufacture, build in quality, make operation foolproof, scale to whatever quantity warfare demands. That philosophy, visible in every aspect of American equipment, had made the outcome of industrial warfare inevitable, long before armies met on battlefields.